All right, welcome back to the Explainer. We're so used to thinking about data in these neat little boxes, right? Rows, columns, tables. But what if I told you the real world is, well, a lot messier? It's all about connections, this huge tangled web of how everything is linked to everything else. Today, we are diving headfirst into that world. We're talking about graph theory.
So let me ask you something. Have you ever been stuck writing one of those monster SQL queries? You know the ones. You're joining table after table after table just to answer what feels like a simple question. Something like, hey, what other products are bought by the people who bought this product? It gets so complicated so fast. But what if there was a better way? A model built from the ground up to answer exactly those kinds of questions?
Well, you're in luck because that's exactly what we're talking about today. We are moving beyond the rigid, boxy world of tables and into something way more intuitive, something that's all about understanding the actual relationships hiding in your data.
Okay, so the big shift here, the real game changer, is what you focus on first. In a traditional relational model, it's all about the things themselves, the rows, the entities. The relationships, you kind of have to build those connections yourself with joins. But in a graph model, the relationships are first-class citizens. They are a core part of the structure right from the get-go. They aren't an afterthought you have to figure out later. They are literally the main event.
So what is a graph, really? It sounds all technical and complicated, right? But I promise you, the basic building blocks are super, super simple. Let's just break it down piece by piece. Okay, don't get scared off by the mathy-looking definition here. A graph is really just two things. First, you've got vertices, or V for short. Just think of them as the dots, the points. And then you have edges, or E, which are simply the lines that connect those dots. That's it, a bunch of dots and the lines between them. And believe it or not, this simple little setup lets us model some of the most complex systems you can imagine. Let's start with the dots, the vertices. You'll also hear people call them nodes. They're basically the same thing. A vertex is just an individual thing, an object. If we're making a map, each city is a vertex. If we're looking at a social network, you and I are each a vertex. It's the noun of our graph, the thing we're interested in connecting. And now for the lines that connect the dots, the edges. You might also hear them called arcs. Now this is where the magic really happens. The edge is the relationship. It's not just pointing from one thing to another, it is the connection. So an edge could be the highway between two cities, or the friendship between two people on social media, or even the purchase that connects a customer to a product. Okay, so right about now you might be thinking, hang on, this sounds a lot like a tree data structure. And you're not wrong, but there's a huge difference. Trees are really strict, right? They have this rigid top-down hierarchy. A child node has one and only one parent. Graphs? Oh, they're way more flexible. They can have loops and cycles. You can follow a path of connections and end up right back where you started. This lets us model all the messy real-world stuff, the complex many-to-many relationships that just don't fit neatly into a family tree. And we can make our graphs even smarter by adding another layer, direction. Think about it. Some relationships are a two-way street, right? Like a friendship on Facebook. If you're friends with me, I'm friends with you. That's an undirected edge. But other relationships are one-way, like on Twitter. You can follow someone without them following you back. That's a directed edge. It's like a one-way street. And this little detail is super powerful for modeling things like, actual traffic flow or who depends on whom in a project. But wait, there's more. We can give our edges even more information by adding what we call weights. A weight is just a number, some data that describes the edge. So if our graph is a map, the weight of an edge between two cities could be the distance in miles, or the time it takes to drive. For a computer network, it could be the bandwidth. And this is absolutely crucial for solving really practical problems, like what's the fastest route, or what's the cheapest connection? Okay, so that's the theory. Dots, lines, directions, weights. But the reason this matters, the reason we're talking about it, is that once you know what to look for, you start seeing graphs everywhere. Seriously, that GPS in your car or on your phone, every single time it tells you the fastest route, it's actually looking at the world as a giant weighted graph and finding the shortest path. Your social media feed, that's a massive graph of you, your friends, and what you're all connected to. Even something as simple as your email. The way it groups replies into a single conversation, yep, that's a graph too. You are literally using graph theory all day, every day, and probably didn't even know it. So this is all great, right? It's a fantastic way to think about things.
But how do we actually get a computer to understand it? How do we take this nice drawing of dots and lines and turn it into something a program can actually work with?
Well, one of the classic ways to do it is with something called an adjacency matrix. It sounds fancy, but it's basically just a grid, like a spreadsheet. Every node gets its own row and its own column. And if you want to know if two nodes are connected, you just look at where their row and column cross. So, if we look at the box where row A and column B meet, we see a 1. That means, yep, they're connected. But where A and D meet, there's a 0. No connection. It's super straightforward. But there's a big problem with this method. What happens when your graph gets huge, like social network huge? And what if most things are only connected to a few other things? You end up with this gigantic matrix that's, well, it's almost all zeros. It's incredibly wasteful. I mean, look at this quote. Trying to represent the entire web this way would require a matrix with 10 to the power of 20 cells. That's no. Just no. It's completely impossible. So, to solve that, we have a much smarter way to handle these big, sparse graphs, the adjacency list. Instead of a giant empty grid, you just take each node and make a list of only the other nodes it's directly connected to. That's it. We're only storing the information that actually matters, the connections that exist. This saves a mind-boggling amount of space and makes everything run way faster.
Okay, so now we have our graph in a format the computer can understand. This is where the fun begins. Now we can start asking it questions, analyzing the network, and uncovering some really powerful insights about how it's all put together.
And we can start simple, just get the lay of the land. How big is this thing? Let's count the nodes and edges. Are there little groups or communities huddled together? We can look for those clusters. And maybe the most interesting question of all, which nodes are the most important? Which ones are the most influential? And to answer that, we need to talk about something called centrality. What's so cool about this is that important can mean totally different things. For instance, degree centrality is basically just a popularity contest. It's the node with the most connections. Think of a big social media influencer. But then you have closeness centrality. That's more about efficiency. It's the node that has the shortest average path to all the other nodes. Think of a major airport hub like Chicago or Atlanta that can get you anywhere else pretty quickly. And this brings us right back to our original problem. This is how you find your most influential customers, or the products that act as hubs connecting everything else. So at the end of the day, graph theory is more than just a data structure. It's a whole new way of seeing the world. It gives us a language to describe all these relationships. Now that you've got the basics down, I want you to think about it. What hidden networks are all around you, in your work, in your social life? What connections could you start mapping out? And maybe, just maybe, understand a little bit better. Hey, if this helped you connect the dots on graph theory, do us a favor and hit that like button. Share it with someone who might find it useful, and of course, subscribe to The Explainer for more deep dives. Thanks so much for watching.